Hello everyone. Today we are going to talk about time marching methods, and so far what we have talked about is mostly um, kind of finding the uh, finite difference approximation for spatial character for spatial by spatial discretization, and what happens. But the question becomes, what happens if we also have a time, like a time derivative in our problem? And so in this lecture, we are going to cover that and also talk a little bit about stability. And then after that, we are going to go more details of this method, and talk about more other methods such as Adams-Bashforth method, Rangakuta a little bit, one stage, much step methods, and other ones, corrected Euler and other time marching methods. Okay, so the title of today's lecture is Approximation for Initial Value Problems or Time Marching Methods. Okay. So to get us started, I want to start with a simple case. So consider a general first order ODE, ordinary differential equation, in time as this: du over dt equals to f u and t, where t is greater than t0 or t naught, and the initial condition of ut at time 0 is just u0. Okay, it's given, and we want to solve this equation, this simple general first order ODE in time. Okay, so the question is, how should we numerically solve for ut? How should we numerically solve for ut? So we talked a little bit about the analytics, and now we want to move forward with the numerical ways. Okay, so a simple way to answer this is, first we need to discretize our domain, similar to the spatial discretization that we did. Okay, so discretize the domain. Okay, so now the difference is we are marching in time, we are progressing in time, right? So I'm gonna have something like this. If this is your time, this is time, so here we have like t0 at time 0, and then here we have t1 at time 1, so we have to discretize it. Then we have t2, and this goes on and on this list. Okay, and this is t. Okay, and this difference between these two values, it is, if we say it is delta t, okay, but I can write it as what, if I am here, I can write it as a forward difference, so it's going to be delta T0, delta T0. If I am here, what's going to be? It's going to be a backward difference, so I'm going to write it as grad T1. And if I'm in the middle, it's going to be a center difference, so it's going to be delta T1/2. Okay, so depending on where you are, these are the notations that we can use for that. And then the next step is approximate du dt and fut using nodal values. Nodal means at nodes of u. Okay, so this is the general approach for kind of dealing with this kind of equations, okay, these ODEs. So there are many ways to do this and approximate this in time, and the simple one of the simplest methods is Euler method, okay, which you can just simply find it out and use it. So we're gonna talk about that now. So let me write it down here. Euler methods. Okay, and the first one I want to talk about is forward Euler approximation. So forward Euler approximation, or explicit Euler method. Explicit Euler method. So these are two names that we have for this method. It's the simplest one, it's explicit, and we will see what does it mean when we talk about implicit methods. Okay, so for this one, it's very simple. So say we have this in time, okay, we have this time progression. And then we have 2 points. One is T0. The other one is T1. And then we just think that we are here. We are seated here. And then we want to do the forward Euler method. So for the forward Euler method, first we have the equation. So the equation tells us what? du over dt minus f over fut minus f, all of that evaluated at t0 equals to 0. And then the second thing we have is the approximation. So we can say du over dt is, we are using a forward Euler method. So I'm going to use delta u 0 over delta t0. Okay, and then we combine these two together and we finally get the Euler, forward Euler method. So I'm going to have u1 at 1 minus u at 0 over delta t0 minus f u at 0 and t0 equals to 0. Okay, So if you do the truncation error, you will see that this is order delta t, and this is the forward Euler method. Okay, so just one thing for just a notation that some people might not follow this, but I think this is useful if you do, is that when you have this u, your variable, okay, we usually, for a space, we put the index at the bottom, and for time, we usually put it at top. Okay, so this is usually show the progression in time, and this can be I, J, K, for example, in different kind of directions like X, Y, and Z. This is in space. Okay, so this is kind of a nomenclature convention that makes it easier to follow, but you might see that some people are using time also at the bottom, like they here, for example, they might say u1 minus u0. Okay, but I think this way it's going to make it more standard, and you can follow this way of kind of nomenclature or convention. Okay, so this was forward Euler approximation. Okay, this is the simplest one that we can have. So the second one is, as you might have guessed, it is backward Euler approximation, or implicit Euler method. Okay, so let's see what is the difference with this one. So here, if you have again this time axis, so here is t0 and here is t1. Now we are seated, and we sit here in t1 and write the equations for here. Okay, so let's see how it will be. So we're gonna have du over dt minus f evaluated at t1 equals to 0, and du over dt is approximated or discretized as grad u at 1 over grad t at 1 and this is going to give me u1 minus u0 over grad t1 minus f u1. Now instead of u0 that we had here, we have u1 here, and t1 equals to 0. This is going to be also order delta t if you calculate that. Okay, so what is the difference between these two methods, forward Euler and backward Euler? So there is a very important difference in stability, which we will cover this lecture, the stability of these two methods. And the other one is, since we don't know this u1, right, fu1, so here is explicit, right? So you have the initial condition, for example, for t0, you know that. So you know fu0, t0, and then you can update u1. You can find the new u, okay, based on the old information. So these are old information. Let me just show that again. So these are, yeah, maybe like this. These are all old information, right? So you can put all of these into the right hand side and then find u1. Okay, so this is explicit. You can easily find that. But for here, we still don't know u1. We don't know what is fu1, right? So in order to solve it, since we don't know we do not know it, we must do matrix algebra. By that I mean we have to have a matrix here and implicitly solve the equations, right? So we cannot explicitly solve it like here, and we have to implicitly solve it because we don't know what it is, and we only know this one, and we have two unknowns. So we have to solve this with matrix algebra. Okay, it has some advantages and some disadvantages. The disadvantage could be that it's more kind of complex method. It's more complex than this explicit one. But the advantage that we will figure it out later is that its stability is higher than forward Euler approximation. Okay, so it's more stable. And by stability, we will come back. What does it mean? It means that the solutions will not blow up, unlike this one, that the forward Euler one, that the solutions might blow up based on different conditions. Okay. So other than these two methods, we have something in between, a method in between, which is called variable weighted Euler approximation. This is just combination of these two methods, and let's see what it is. So the method is as follows. We have again the time axis, we have the time axis here. T. And we have T0 here. And T1 here. What I'm going to choose is something in between. So I'm going to choose something like here. T star, which is T0 plus theta delta T. Okay. So then du over dt, I can write it as, approximate it as u1 minus u0 as delta t at delta t0. And for f, I'm going to evaluate it at ut star and t star. Okay. So what I'm going to have is this. I'm going to have u1 minus u0 over delta t minus so for this one, this is going to be what? This is going to be, I'm going to say it is theta f evaluated at t1 plus one minus theta f evaluated at t0. Right? So this is how I write it down. So then I'm going to write it as theta f u1 and t1 plus 1 minus theta f u0 and t0 equals to 0. Okay, so let's investigate this. If theta is 0, this means we are here, right? We are at t0. Then this is gonna give me, if you also look at it here, this term is gonna be 0, and we only have this one. So we are gonna have a forward method. Okay, if theta is 1, this is gonna be 0, and then we are gonna only have this one, and so this is gonna be a backward method. And if theta is in between, for example, 1/2, these are the new ones, which we didn't have before. And for theta equals to 1/2, we call it Crank-Nicolson approximation. So this one is going to be order delta t squared. So these are order delta t, order delta t, but the last one is going to be order delta t squared. Okay, so this is a variable weighted Euler approximation, which is essentially a combination of forward and backward Euler method. Okay. So the next thing I want to do is to look at the stability of these methods and see whether they are gonna their solutions are gonna blow out in time or no.